Jnanam Paramam Dheyam. Knowledge is supreme.
Hello students, welcome to this course on chemical process control. The topic for this first week will be Introduction to Process Dynamics and Control. Let us get started with Introduction to Process Control. Here are the objectives for this particular part of the lecture. At the end of this lecture, you should be able to articulate what is the need of process control, what are the different functions a process control system performs when it is implemented in a chemical plant, what are the different elements of a control system, what are the different types or the control strategies which are possible and what are their advantages and disadvantages. And lastly, we will also look at what are the different types of control problems which exist in a chemical industry. So, let us get started. Chemical process control is one of the core courses in your chemical engineering curriculum. You also take different courses such as heat transfer, reaction engineering and other courses. In these different courses, you might have come across design of various chemical engineering equipment. So, just try to look back at what are the different types of assumptions which you make while designing any equipment for a chemical plant. Let us take an example from heat transfer. Let us consider that you are designing a heat exchanger so that you cool a process stream which is available at 100 degrees C and you have to cool it all the way up to 80 degrees C. This can be done by passing a cold fluid from the other side of the heat exchanger. So, let us say you have cooling water which is available at 30 degrees Celsius and so the requirement originally is you have a hot stream which is available at 80 degrees 100 degrees Celsius and you want to cool it all the way up to 50 degrees Celsius, and you have a cooling water which is available at 30 degrees Celsius. So, you can do the calculations for this exchanger and eventually you will find out what is the UA requirement for this particular exchanger, and accordingly you will find out what is eventually the area of the exchanger and you will buy an exchanger according to that particular area as well as UA specification. Now, let us think that if you put that exchanger in real plant, would it always give me 50 degrees Celsius as the outlet of the hot stream? It will give you that provided your hot stream enters at 100 degrees, your flow rate of the hot stream remains constant at the value which was designed. Also, your cooling water is available at 30 degrees Celsius. However, all these assumptions are not always possible. It is not always possible to maintain all these assumptions when the plant is actually operated. When you design a plant, you always design it at non-fluctuating or constant properties such as the feed conditions, feed temperature, flow rate, feed composition, as well as the external parameters being constant like the cooling water temperature. However, when you operate the plant operation is quite dynamic and it is subjected to various disturbances. So, let me show you a simple simulation highlighting what happens if you have the cooling water temperature rather than a constant assumed value of 30 degrees. Let us take how a real life cooling water temperature would vary. So typically cooling water comes from a cooling water tower, and the temperature which you get is typically dependent on the ambient temperature. And you all know that during the day as well as night, the ambient temperature does indeed change, and here you can see that the cooling water temperature cannot be maintained exactly at 30 degrees as which was the assumption for our design, and it does change throughout the day as well as night. So accordingly, if such a cooling water temperature is available for the heat exchanger, the outlet which comes out from the exchanger, the hot side, will never be exactly equal to 50 degrees. However, it will also oscillate like the, or it will also change depending on how the cooling water temperature is changing, and what you get at the end is an average performance which is similar to what we have designed. However, the local or the instantaneous temperature of the hot stream does not guaranteed to be at 50 degrees. So, if this particular stream is going to a different unit operation, let us say it is going to a separation system which requires the inlet temperature of 50 degrees, then we are not able to maintain that particular inlet temperature. So, the take home message is the operation, the actual plant operation is quite dynamic because it is subjected to various process disturbances, environmental disturbances, as well as there are in some cases, even though you design a system at a particular operating point, due to different changes in terms of market conditions or different changes in the topology of the process, you want to operate the process at a different operating condition. So, you want the plant to move from one point to the other, and thus there are changes in the desired operating point. So, in such cases you do not go about changing the design every time, because it is not always feasible to change the design of a process every now and then. So, what you end up doing is you implement a system which will ensure that irrespective of such disturbances as well as fluctuations, what you get out of the process is same as what was the original objective. So, the aim of and this is the job which a process control system does. So, the aim of the process control system is to maintain the operation of the actual plant close to whatever is your desired point. So, now control is a very commonly found theme. So, process control deals with control of chemical engineering processes, but in general control is a very common phenomena, and let me motivate it through some of the household common control examples. So, the first example I am going to take is of taking shower. So, let us say you take shower every day and you typically try to have some feel good temperature as well as feel good flow rate of water when you try to take bath, and you are typically provided with two sorts of nozzles or two sorts of valves. So, you can change the flow rate of cold water as well as hot water, and accordingly you mix them such that whatever water you get out of the shower has the required temperature as well as the flow rate. So, here the objective is that you want a certain temperature as well as flow rate of the water coming out of the shower. The other example is a pressure cooker. So, when we cook, we typically want to cook it at a higher temperature, and thus we want to maintain a certain pressure inside the pressure cooker. So, how do we maintain that? The way our pressure cooker works is, if the pressure of the steam inside the cooker increases or reaches the value which we desire, then the whistle gets blown up. So, as the whistle opens, the steam goes out and suddenly the pressure starts dropping. As soon as the pressure reaches the lower value, the whistle again goes back. So, that way by having the manual whistle, you are able to maintain pressure inside a pressure cooker. The next example is crossing the road. So, when we want to cross the road, we typically have an objective that we want to go from one end of the road to the other without getting hit by any vehicle, obviously. And what happens is we have control on how fast we can go and when we can we cross the road. And the disturbances here are the cars or the other vehicles are coming from both the sides. So, we have to ensure or we have to predict whether we are able to cross the road without being hit. So, in that case you try to predict how fast the car is coming, how much time would it take till it reaches you, and accordingly you try to calculate whether you would be able to cross the road or not safely. And lastly, all of us have air conditioner at home, and the job of the air conditioner is to maintain the temperature which we set through its remote. So, if we set a particular feel good temperature for the room, then it is the job of the air conditioner is to maintain that temperature irrespective of whatever is the outlet temperature or how many people are inside the house. So, in a way it tries to maintain that temperature by manipulating its operation. So, in the end, through all these 4 examples, you can see that every control system has an associated objective with it. So, if you take the shower example, here we want to maintain the temperature and flow rate. In the case of cooker example, we want to maintain the pressure. In the case of crossing the road, we want to cross the road without getting hit or cross the road safely, or in the case of air conditioner, we want to maintain a constant temperature. So, similarly, when we talk about process control, then these objectives are related to the process. So, if we have a chemical plant, then the control system will be used to satisfy some of these objectives as well as some of the constraints. So, let us again try to pause and think about, if you are operating a chemical plant, what are the different types of, or what are the different objectives which an operator has to maintain. So, first and foremost, as the process or a chemical plant has been set up to make money, then the primary objective of operating a plant is to make profit. Now, if you have to make profit out of a chemical plant, you have to make sure that whatever the product which you are making meets the specification. So, if your product does not meet specification, then there is no way you can generate profit out of that plant. So, another operating objective is to make sure that your product meets the desired production specs. The other thing which you might want is you are not gonna make the product only once. You purchase an equipment and then you want that equipment lasts its lifetime, like 10 years or 15 years, and that can only happen if you take good care of your equipment. So, while making product out of your plant, you also want to make sure that you are protecting the equipment, you are not running it towards its limit, so that you can take your plant or you can use your machinery for a very long time. While doing all this, you also have to make sure that you are not polluting the environment, because that is what eventually even you are going to live in. So, while achieving profit as well as production spec, you also have to keep one eye towards meeting environmental regulations. And lastly, you also have to do all this within a safe environment. You cannot subject your workers or your labor or also the surrounding people who are living around your plant. So, their safety is also important. So, when you are operating a chemical plant, you have to ensure that these are the different operational objectives or constraints within which you have to operate. So, as per, if you connect the 2 slides, we should have some sort of control strategies which will take care of all of these. So, before moving forward, let us see whether these objectives which we talked about, are all these objectives taken care of in the same order, or there is a special hierarchy in which these different objectives have to be satisfied. So, as it turns out, this is the hierarchy in which these different decisions or constraints are to be satisfied. So, first and foremost, the plant or the operator has to ensure the safety of the personnel who are working inside the plant, as well as those who are around the plant. So, the safety of personnel, equipment and environment takes always a prior for the first seat. Once you ensure that the plant is safe to operate, you try to make sure that the product which you are getting out is of required grade. Then you also try to minimize whatever is the burden on the environmental system. So, you want to ensure the specs while minimizing the effluent which goes to the effluent treatment. Then you look at elongating the life of your equipment by trying to ensure that all the equipment operate within their safe limit. And once all these things are ensured, then try to look at improving the profit. So in a way, even though your primary objective of operating a plant is to make money, it typically comes as the last layer of your operational constraint, and there will always be a control system associated with all these different layers. So let's say if you are a plant operator and you have to ensure all these things, then in order to have in order to ensure whether the plant is safe or whether your product specifications are met or not, what you need to know is where are you currently standing. If you want to ensure safety, you want to know that how far I am away from the safety, or if you want to ensure that the product specs are met or not, you want to know what are the current product spec and how far you are away from the boundary. So all that requires an eye into the system, and that is done by doing what is known as process monitoring. So you have to have installed different instruments inside the plant which will give you a measurement about how or what is the current state of the process, whether it is close to any operational constraint or it is away from the constraint. And once you know where your system is at, then and you know what is your target performance, then you can take some action and then move the plant from your current point to the desired point. So that becomes the role of process control system. So as we have multiple constraints or multiple different layers or hierarchy of objectives, even the control system in a chemical plant also has lot of hierarchies. So here is a typical hierarchy of process control activities in a chemical plant. So at the bottom layer is your actual process, and the first thing is the measurement and actuation. So these are all the equipments or instruments, these are all the instruments which are put into the system either to read value from the process or to take some action on the process. So these are the hardware elements inside the process, and they will operate at a very fast rate, let us say at a second level or at the time interval of few seconds. And on top of that, the first and primary layer of control is the safety logic. So this is the fallback or the primary safety which is inbuilt into the system. So irrespective of whether you have an additional control system or not, this particular safety logic will always ensure that your system cannot violate any basic safety boundaries. So for example, in the cooker example, in the example of that steam pressure cooker which I showed you, the pressure cooker also comes with a safety valve. So if there is some problem in terms of the whistle and the whistle does not open or close, gets blocked, then there is always a rupture disc which is on top of the cooker, which will open if the pressure reaches some unsafe limit. So as soon as that happens, irrespective of whether the whistle is working or not, the burst disc will burst and then the pressure will be released. So every chemical system will always be associated with some sort of safety logic which will ensure that even though there is no control system or the control system fails, that particular logic will ensure safety of the plant. Now on top of that is the first level of control which you ensure, which is a regulatory control. So these are the basic control actions which are taken, and those will be taken at the frequency of few seconds. And then there are other advanced control strategies which are on top of that, which will subsequently ensure additional objectives. So first, primary regulatory control will try to ensure the basic objectives of the control system, and then as you go above this particular hierarchy, then you will move towards making more profit out of the plant. So let me explain all these hierarchies for a simple example of CSTR, which is going to carry out a reaction which is going to generate some gaseous product along with a liquid product. So let us say this is the reaction which is getting carried out in this CSTR. So this is how your feed comes in. There will be a feed valve. there will be one product valve for B, and there is also some gas getting generated. So, there will be a gas valve here and this is an elevated temperature reaction. Exothermic. So, in order to maintain temperature, you would have to have some cooling inside the system. So, this is a system for which we will look at what are the different hierarchies of the control system. So, this is our process. So, the main process I can simply highlight as this, which includes reactor and jacket. Then we will have measurement and actuation. So, here the measurements would be of pressure inside the reactor, the measurement can also be temperature inside the reactor, it may be composition of the product which you are getting out. In terms of actuation, you may have different feed flow valves and you may have some product valves. So, this is how the system can be actuated. Now, the first and foremost is a safety control logic. So, in this typical example, what you would want as a safety precaution is that the pressure inside the reactor should not blow up if there is unnecessary production of C. So, in that case, what you want to ensure is if the pressure inside the vessel goes to a very high value, there should be some safe route, and that is typically achieved by having something known as a pressure relief valve. So, you typically have a pressure relief valve as a safety precaution, which will ensure that if the pressure inside the reactor goes to a very high value, then it will open up and have a safe release of the gaseous product. Then we move on to the regulatory layer. So, regulatory layer is the basic control system which has to operate or which has to take decisions of maintaining the operation at a time frame of few seconds. So, typically for this particular system, it will involve controlling the temperature. So, we typically represent it as TIC, which refers to temperature indication and control. So, the regulatory layer will ensure that the temperature inside this reactor is maintained at a particular level. This is done by manipulating the cooling water flow rate by using this particular actuation. And the idea here is, if I maintain a particular temperature in this reactor, then we are also somehow ensuring that if all the other conditions remain the same, then even the conversion or the product purity remains more or less at the same value or the desired value. Then the next level of control is the supervisory control. Now, even though we are controlling temperature at the regulatory level, our main objective out of this reactor is to get a product of required purity. So, what we want is a particular composition to be maintained at the desired value. So, your composition control will come at the supervisory level, and what it will do is it will try to dictate how the temperature controller loop change operates, so as to ensure a particular value of the composition. And then we go on to the higher value. So, let us say if we talk about the real time optimization. It will try to find out what is the best value at which this particular composition should be maintained, so that I minimize the cooling water or I maximize profit. And then lastly, when we talk about the planning and scheduling level, it actually looks at what are the market conditions, what is the demand, what are the raw material cost, and accordingly it tries to predict at what particular time which particular product or what particular purity has to be maintained, how much amount of product has to be produced. So, all that planning type of decisions are taken at the higher level. So, with this simple example, we have what we could see is there are different objectives in a chemical plant, and there is no single control system which maintains all these objectives. There is always a hierarchy of decision making and hierarchy of control systems, and each control system has an associated hardware with it and an objective associated with it. So, we will take a short break, and when we come back we will look at what are the different functions of a chemical or control system. Thank you.